Well, so the Green's theorem, it's a line integral in which circulation and flow, because there's actually two versions of Green's theorem. That is one that involves circulation and another one um, that involves the other one flux. All right. Well, so let's see. So the circulation of a vector field f along some curve, it's a measure of how much of the vector field points in the direction of c. For example, in this case, I have a few pictures here. Consider the second case. There is some portion of the vector, because check this out, not the whole vector is going in the direction of the circle. It's only a portion of it. Remember projections? So only part of that vector is actually contributing to the work of moving a particle along the circle. So that's one case. In this case, because notice these orthogonal vectors. These vectors are pointing out of the circle, and in this case, those vectors are not moving any particle, and they're not moving any particle around the circle. In fact, this is like these are actually trying to put the particle outside of the circle, And well, that happens sometimes. Well, as a real world relation, when you're on a plane, when you're landing on a plane, and sometimes you feel a lot of turbulence while landing, and that's because there's some crosswind that's going at some angle with respect to the path at which the airplane is landing. In some cases, even perpendicular. So that's why sometimes airplanes have to land on another direction, or that's why sometimes some of the airports have like multiple runways in different directions. Like the Chicago airport has like 9 or 8 runways pointing in many directions, because the wind city, right? It's very unpredictable what direction will the wind take in Chicago. And well, airports are actually designed based on the most common airflow, so that airplanes don't encounter this crosswind. So you cannot just build a runway and land, So there's actually these kinds of studies in order to get that done, right? And well, of course, those vector fields. Those vectors push a particle or some portion of those forces, actually, and that's the circulation. The circulation is how much of the force is applied onto the particle moving along a circle or any other path. It doesn't have to be a circle. The circle is just the best. The simplest case. And then of course these are unit tangent vectors. Remember big T? Well, we're not going to compute any of those. Recall that we redefined that f dot big T ds into fdr to compute it a lot easier. So other examples, more generalized examples. Check all these vectors right here. These vectors, well, are neither tangent nor completely orthogonal. So that means there's some projection here, some portion of that force onto the path right here. And in the other situation, these vectors are not totally, well, this is f onto tangent vectors. So we're going to compute the value of that integral, which is related to the circulation. But well, let's see. Green's theorem and curl. So a curve C given by R of t, which is some x component with respect a function of t, and a y component, which is a function of t, and within an interval a and b. Well, it's simple and does not cross in itself. So that is, it's just a curve. It doesn't create it doesn't cross itself to create like a loop, something like that. No, it is simple, and well, Green's theorem tells us that if R is a simply connected region with a piecewise smooth boundary C, or we enter counterclockwise, this is very important. This has to be, the region we're going to go about has to be oriented counterclockwise. All right? That is, C is traversed once so that the region R always lies to the left. And assume big F, which is fg, you know, that's the gradient, and that's the gradient of a function where f and g have continuous first partial derivatives. Well, so instead of parameterizing, instead of finding the potential function, we are going to take partial derivatives of the gradient, find the difference between them, and evaluate the double integral, which is going to be a lot shorter, right? So this form of the Green's theorem is also called the tangential form or the curl form, and that's because that deals with the circulation. We're going to look at a second form of Green's theorem, which deals with the normal, that is, which is called the normal version, which is the divergence version, which deals with vectors that point out of the region. In other words, that deals with flux, not circulation. So just to give you a picture here, well, not this one. All these vectors that I'm going to draw here, the ones in green, these are tangent vectors, unit tangent vectors to be more specific. These vectors describe the circulation, while the other vectors that I'm going to draw here in a different color, that's the flux vectors, and those point out of the region. All right? I mean, that flux outside or inside, I mean, we have a source or a sink. Well, actually, let's not get into the details about curl and divergence. We're going to get into the details later in the next section. So for now, let's just look at Green's theorem, and we can actually evaluate what we're going to do. We are to evaluate the line integral using a double integral by means of Green's theorem. Now, this quantity that you see here in the double integral, this difference of the partials here, this is called the two-dimensional curl. All right, that's the two-dimensional curl, and that's what describes the circulation. And well, in the following the next section, which is 17.5, we're going to look at these properties of curl and divergence, and we're going to look at their versions in 3 dimensions. All right, so we're going to go back to a lot of partial derivatives, and then we will finish the course looking at the last 2 integral theorems. All right. So whenever the curl is 0, that is, this difference of the partial is 0, well, then we say that the vector field is irrotational. So the vector field is not rotating, it's actually rays pointing out from the origin. You might remember those pictures of vector fields at the beginning of the chapter. We draw the graphs of some of them were rotational, some of them were rays, like having a source of energy from the origin, or a sink. Well, I don't think we look at the case of the sink. We just look at the source. So, but again, the rotational properties of these vector fields, we're going to look at them more in detail in the next section. In the meantime, for examples 1 through 5, let's use Green's theorem to evaluate the line integral. Draw a picture to represent the region. And again, number 1, if the region that they are giving us is not closed, we cannot use Green's theorem. Green's theorem, again, only works when our regions are closed, and we'll orient them in a counterclockwise direction. So number 1, let's have a look. So evaluate the integral to xy dx plus x plus y dy, where C is the boundary of the region lying between the graphs of y equals to 0 and y equals 1 minus x squared. Let's find out whether that region is closed. All right, so Cartesian plane, the graph of 1 minus x squared, that's a parabola upside down, pointing upside down, and shifted 1 unit up. So that's 1, 2, 1, 2, and so that's our parabola. And we also have y equals to 0, which is this horizontal line. Does that look like a closed region? It is, right? It is a closed region. And we also want to make sure that that this region is going counterclockwise. So yes, the conditions for Green's theorem are satisfied. Oh, again, okay. So before looking at the example, so I really don't want to miss that that definition of really the physical definition of, or the geometric definition of Green's theorem. So all these points that are inside this region. So I have this point. I have another point, many points. So what this integral does, because what does the integral do? I mean, geometrically speaking, is to add infinitely many areas. A double integral adds infinitely many rectangle areas. This double Green integral, or Green theorem, which is this double integral, well, let me zoom it in. So suppose for this point, I can find all the circulations around this point, you know. It's kind of hard to draw it. So, well, let me make this bigger points so it's easy to. So this tangent vector right here is the circulation on one point. All right. So what this double integral is doing is to add all those infinitely many circulations into a single one, in the same way that we derived a formula to find the area under the curve. Well, this is all the circulations inside of a region. All right. For the other form, which I don't think we'll get the chance to do today, well, that's a similar explanation, but you'll see. All right, so okay, so we want to evaluate this integral, this line integral to xy dx plus x plus y dy. This is equal to the double integral over the region R of the partial of g with respect x minus the partial of f with respect y dA, where dA, again, that's going to take us back to double integration, whether our region over there, the one that we have in 2D, is vertically simple, horizontally simple, you know. So number one, let's find these two partial derivatives. So f, that's 2xy, and g, x plus y, partial of f with respect y, that's 2x, and partial of g with respect x, that's 1. So all we have to do here is evaluate this double integral over the region R of 2x, 1 minus 2x. And well, this dA, again, we set up the order dy dx or dx dy depending on whether this region is vertically simple or horizontally simple. And typically we go dy dx because, check this out, we're given functions of x, and in fact this region happens to be vertically simple, isn't it? So double integral, and that's going to be 1 minus 2x dy dx. Okay, so the limits The limits in the y direction are the upper function, which is 1 minus x squared, and the lower function, which is 0, and the limits in the x direction go from -1 to 1, because those are the points of intersection that goes from -1 to 1, right? On the picture, or you can find them algebraically, but I think the picture it's pretty clear, and I would accept this. I mean, you don't have to find them algebraically. That's fine. And let's evaluate this integral first with respect y. So that's the integral from -1 to 1 of y minus 2xy evaluated from 0 to 1 minus x squared dx. So that's the first iteration of the integration. Let's do the second iteration. Fundamental theorem first. And again, the limits of integration will get plugged in only in y. All right? Because we integrated with respect to y. So that's equal to the integral of -1 to 1 of y, which is 1 minus x squared minus 2x times y, which is 1 minus x squared dx. And now we end up with a single variable, with a single integral that depends only on x. And doing some simplifications, this should be the integral from -1 to 1. That's a 1 minus x squared minus 2x plus 2x cubed. And well, we can integrate this polynomial. There's no like terms to combine. After integrating this, because it's going to take a good minute to go, that should be 4/3. Did we have to parameterize anything here? Nothing. Did we have to find a potential function here? No potential function. Number 2. Let's do number 2. Integrate e to the x cosine to y dx minus 2e to the x sine to y dy over the pad, the closed pad, which is x squared plus y squared equals a squared. Well, that's just a circle of radius a. We don't know what that radius is, but actually it's not going to matter. You'll see why it's not going to matter. So, and again, it doesn't have anything to do with independence of the pad, because that's not what we're looking at this time. So that's a negative a, negative a, and a. And let's make sure that this is oriented counterclockwise. Oops. All right. And okay, so it's oriented counterclockwise. And in this case, well, let's identify our f and our g. So f and g, and let's find their partial derivatives. So the partial derivative of f with respect y is e to the x, the derivative of cosine, which is negative sine, of 2y times by chain rule times 2, but this is negative. And also the derivative, the partial derivative of g with respect x, that's going to be, careful, because the derivative of e to the x is just itself times 2 times sine to y. Well, that remains the same essentially, to e to the x sine 2y sine to y. All right? And, well, so we can find the line integral, that is, the line integral over the closed region. That's how we denote that with the circle in the middle of the integral sign, over the region C of f dr. And in this case, that's the double integral of partial of f with respect y, the reverse, partial of g with respect x, minus partial of f with respect y. and that dA. But do you notice these two are actually the same? Subtract them, and that's going to be the double integral of r, and that's negative 2e to the x sine 2y minus negative 2e to the x sine 2y, sine 2y rather, dA. Oops, I think I need to move this a little bit. Oops, oh no. And this is dA. However, what is that going to give us? 0. And the integral is 0. Well, if we still connect with the material from before, most likely this f and g, which form the gradient of some potential function that is the big F, most likely this is a conservative vector field that contains or that has a potential function, but because we're doing an integral over a closed region from point A to point B, which happens to be the same, it's a closed integral. That's the third implication, isn't it? That the integral is 0.